Early morning light spreads across Lake Tahoe, but something about the lake feels wrong. At first, it's subtle, a quiet shift that most visitors don't immediately notice. The water line along the shoreline is creeping higher than usual. Wooden docks that normally sit comfortably above the surface are suddenly kissing the water. Then the readings come in. A monitoring station near Tahoe City records the number first, 6,229 feet. The figure flashes across the screen. For a moment, technicians think it's a sensor error. The lake has risen before during wet seasons, but this number is pushing dangerously close to a level rarely seen in modern records. Within minutes, a second station confirms it. Then a third. Lake Tahoe has surged to 6,229 feet above sea level. Along the shoreline, the effects began appearing almost immediately. Small beaches that tourists stood on the day before are now underwater. Waves roll farther inland than usual, slapping against retaining walls and creeping toward lakeside properties. Boat owners rush down docks, pulling ropes tighter as vessels began rising higher than expected. But it's not just the water level that's changing. Sensors positioned around the basin begin reporting something else, tiny vibrations. At first they register as background noise, barely noticeable movements deep underground. But the pattern is strange. The tremors are clustering along known geological fractures surrounding the lake. Technicians stare at the seismic feed as faint lines begin appearing on the monitors. One tremor, then another, then a cluster. Each one small, barely strong enough to be felt by people standing on the ground. But the location catches everyone's attention. A movement is occurring near the West Tahoe Fault, one of several major fault systems that frame the massive lake basin. Outside, the lake looks calm. Tourists continue taking photos of the water, reflecting the Sierra Nevada peaks. Kayaks glide across the surface. But inside monitoring centers across California and Nevada, scientists are suddenly leaning closer to their screens. Because the surge to 6,229 feet is doing more than raising the shoreline. It's increasing the weight pressing down on the lake bed itself. And deep beneath the water, the ground is beginning to respond. The moment the number stabilizes at 6,229 feet, phones begin ringing across multiple monitoring centers. Inside the U.S. Geological Survey Seismic Lab, analysts are already watching the screens when the alert arrives. Lake-level data from Tahoe's gauge network confirms what they feared. The surge is real, and it's happening faster than seasonal models predicted. Within minutes, the information spreads through emergency channels linking California, Nevada, and federal geological agencies. Technicians begin pulling up historical charts. Lake Tahoe has risen before. Heavy snow years have pushed the water level upward many times, but today's reading is different. The lake is now approaching a level that dramatically increases the pressure on the basin floor. That pressure matters, because Lake Tahoe is not just a scenic alpine lake. It sits inside a deep geological bowl shaped by ancient fault activity. The basin itself was formed by movements along fractures that still exist beneath the region. Those fractures are not completely dead. They are quiet, dormant, but not gone. In the USGS control room, a cluster of red dots begins appearing on the seismic map around the lake's western edge. Micro-tremors, small movements, barely registering above magnitude 1.0. Normally, these would barely attract attention. The Earth constantly shifts in tiny ways. But what alarms scientists is where the tremors are happening. They are lining along a known fault system that runs parallel to Tahoe's western shoreline. A senior seismologist leans forward, scanning the data stream. Another tremor appears. Then another. A pattern is beginning to form. The timing is unsettling. The tremors start within hours of the lake reaching 6,229 feet. At the same time, hydrologists monitoring inflow from surrounding mountain rivers report something equally concerning. Snowmelt from the Sierra Nevada has been pouring into Tahoe faster than expected, driven by an unusually warm spring following a record winter snowpack. The lake is not just high. It's still rising. Emergency coordination calls begin forming between agencies in Sacramento, Carson City, and Reno. Officials want to know whether the rising water could interact with the region's complex fault system. The answer scientists give is cautious, but not comforting. Water itself doesn't cause earthquakes, but the weight of billions of tons of water pressing on a fault system can sometimes alter stress underground. And if a fault is already near its breaking point, even a small change in pressure can matter. Outside, Lake Tahoe still looks peaceful. But inside geological monitoring centers, one phrase begins circulating quietly among researchers. The lake is loading the faults. To most people standing on the shoreline, Lake Tahoe looks timeless. A deep blue mirror surrounded by towering pine forests and the granite walls of the Sierra Nevada. But beneath the water, the landscape tells a very different story. Lake Tahoe exists because the ground here once tore apart. Thousands of years ago, powerful movements along the Earth's crust began stretching the Sierra Nevada region. Massive blocks of land shifted along deep fractures known as normal faults. One block dropped downward while the surrounding mountains slowly rose higher. The result was a giant geological basin. Over time, snowmelt and rainfall filled that basin with water, creating what is now one of the deepest alpine lakes in North America. But the fractures that created Tahoe never disappeared. They remain locked beneath the lake and along its surrounding slopes. One of the most significant is the West Tahoe Fault. This fault stretches for more than 50 kilometers along the lake's western edge, running beneath forests, mountain ridges, and sections of the lake bed itself. Geological studies show that this fault has produced powerful earthquakes in the distant past, events strong enough to reshape parts of the basin. The problem is that faults like this do not move on predictable schedules. They can remain silent for centuries, then suddenly shift again, and Lake Tahoe sits directly on top of several of them. Beneath the water, the basin plunges to depths of over 1,600 feet, meaning the lake holds an enormous amount of weight, pressing downward onto the crust below. Under normal conditions, the Earth's crust slowly adjusts to that pressure. But when water levels rise significantly, that pressure increases. The concept is simple. Water is heavy. Every additional foot of lake level means billions of gallons of water pushing down on the basin floor. And that pressure doesn't just sit on the surface. It transmits downward through rock layers, fractures, and sediment deposits that fill parts of the lake bed. In certain conditions, that pressure can seep into existing faults. When water infiltrates fractures deep underground, it can slightly reduce the friction holding two blocks of crust in place. Scientists call this poor pressure water pushing into microscopic spaces inside rock. When pore pressure rises along a fault that is already under stress, it can weaken the locking force that keeps the fault stable. Most of the time, nothing dramatic happens, but in rare situations that added pressure becomes the final trigger. A fault that has been quietly building tension for decades or even centuries can suddenly slip. And now, with Lake Tahoe reaching 6,229 feet, scientists are beginning to worry about exactly that scenario. Because the basin is not just holding more water than usual. It's applying more weight than the underlying faults may be used to carrying. And the tremors that have started appearing around the lake suggest the ground beneath Tahoe may already be adjusting. By midday, the quiet concern inside monitoring centers turns into focused urgency. Seismic stations scattered across the Sierra Nevada begin recording a steady stream of tiny movements beneath the Lake Tahoe basin. At first, the tremors are weak, so small that nobody standing on the ground can feel them, but the instruments can. Each sensor buried in the rock sends a continuous stream of data back to regional monitoring centers. Lines ripple across computer screens as the earth vibrates in short, sharp pulses. Another tremor appears, then another. The pattern is no longer random. Clusters of micro-earthquakes begin forming along the western side of the lake, tracing a subtle line that runs beneath forests and mountain slopes before disappearing under the deep blue water. Scientists recognize the pattern immediately. It follows the West Tahoe fault system. The magnitudes remain small, most between 1.0 and 2.3, barely strong enough to rattle a window. But the frequency is rising. Within hours, the count climbs past 20 separate tremors. Seismologists start mapping the epicenters. The points on the map begin lining up almost perfectly along the fault's known trace. That alignment is what worries them, because when faults begin to wake up, they often start quietly. A series of tiny adjustments as the crust slowly redistributes stress along the fracture. Sometimes the activity fades just as quickly as it appeared, but sometimes it builds. Inside the monitoring lab, analysts compare the tremor timing with lake-level data. The correlation is unsettling. The seismic activity begins just after the lake crosses the 6,229-foot threshold. At the same time, pressure sensors installed near the lake bed detect slight shifts in subsurface stress. Nothing catastrophic, yet just subtle changes in how the underlying rock layers are responding to the added weight above. Still, the signals are enough to trigger heightened monitoring. Additional instruments around the basin are switched to rapid sampling mode, capturing more detailed readings of ground movement. Meanwhile, scientists begin running real-time models to estimate how the rising water might be interacting with the region's fault systems. Outside the lab, life around Lake Tahoe continues almost normally. Tourists fill lakeside restaurants. Boats cut across the bright blue water. Families walk along shoreline trails without noticing anything unusual. But deep underground, the story is different. The earth beneath Tahoe is shifting in small, restless movements. Each tremor is a tiny release of stress, and together they form a signal that geologists recognize all too well. Sometimes when faults begin to whisper like this, they are preparing to speak much louder. By late afternoon, the tension that began inside scientific labs starts spreading to the communities surrounding Lake Tahoe. At first, the warnings move quietly. Local officials receive briefings from state geological agencies. The message is cautious but clear. Lake levels are unusually high, and seismic monitoring has detected a growing cluster of tremors beneath the basin. No evacuation orders, no emergency declaration, but authorities want residents to stay alert. Along the shoreline towns Tahoe City, South Lake Tahoe, Incline Village, and Kings Beach, word began circulating through local radio stations and emergency notification systems. Most people hear the announcement while going about their normal day. Some pause. Others shrug it off. After all, Lake Tahoe has always been known for dramatic weather and heavy snow years. Rising water levels don't immediately sound like a disaster, but lakeside property owners start noticing something unusual. Water that normally sits several feet below retaining walls is now creeping higher along the shoreline. Dock posts disappear deeper into the lake. Wooden piers that once stood above the waves now look almost level with the surface. Boat rental operators scramble to adjust mooring lines. Marinas begin moving vessels farther from crowded docks as the lake pushes closer to infrastructure not designed for these levels. Then the tremors begin to reach the surface. At first, they're barely noticeable. A faint vibration, a glass rattling for half a second, a hanging light swaying just enough for someone to glance up in confusion. In a lakeside cafe near Tahoe City, a few customers pause mid-conversation as the floor seems to hum beneath their feet. It lasts only a moment. Then it's gone. Outside, nothing appears damaged. Cars remain parked. Buildings stand untouched. But seismic sensors register the event clearly, a magnitude 2.6 tremor along the West Tahoe Fault. It's still small, but it's stronger than the earlier ones. Local emergency management teams begin quietly preparing contingency plans. Fire stations review response procedures. Search and rescue teams check equipment. Hospitals receive early notifications in case a larger seismic event occurs. Meanwhile, thousands of visitors continue filling the lake's beaches and hiking trails. Many of them have no idea that scientists are now watching the region with growing concern, because while the tremors remain minor, the lake level continues creeping upward, and every inch of rising water adds more weight pressing down onto the fragile fault system beneath Tahoe, a pressure that the earth may not be finished responding to. As evening approaches, the situation around Lake Tahoe begins shifting from quiet concern to active preparation. Inside regional emergency coordination centers, maps of the Tahoe Basin fill large digital screens. Colored overlays mark population centers, evacuation routes, and critical infrastructure surrounding the lake. Officials are no longer just monitoring the situation. They are preparing for what could happen if the ground moves harder. The Tahoe Basin holds tens of thousands of residents, and during peak tourist seasons, well over 100,000 people can be present in the region at once. Roads winding through the mountains were never designed for rapid mass evacuation. That reality now becomes part of the conversation. Emergency planners begin reviewing traffic flow models along the two primary escape corridors, Highway 50 and Highway 89. If a larger seismic event strikes, landslides could easily block sections of these routes within minutes. And that's not the only concern. Several small dams and water control structures regulate the lake's outflow near Tahoe City. These systems are built to manage seasonal fluctuations, but they were not designed with a sudden combination of elevated water pressure and seismic activity in mind. Engineers monitoring those structures now begin running rapid stress calculations. So far, the numbers remain within safety margins, but the margin is shrinking. At the same time, utility companies begin inspecting power lines that snake through steep mountain terrain surrounding the basin. An earthquake, especially on the West Tahoe Fault, could trigger rockfalls or tree collapses capable of cutting electricity to large portions of the region. Hospitals quietly review emergency surge capacity. Fire departments prepare equipment for potential structure collapses or shoreline flooding. Search and rescue teams stage vehicles closer to key population areas. Yet outside these planning rooms, the lake still appears calm. The surface reflects the fading orange light of sunset as boats glide back toward marinas. Restaurants along the shoreline fill with evening diners. But in monitoring centers across the region, one piece of data refuses to stabilize. The tremor count continues climbing. 30 events, then 40. Each one small, but each one happening along the same restless fracture beneath the basin. And beneath the rising water of Lake Tahoe, the pressure building along those faults has not yet reached its final limit. Night falls over Lake Tahoe, but the monitoring centers remain fully lit. Inside the seismic lab, screens glow with live data streams from dozens of sensors scattered across the basin. Every vibration, every shift in the ground is being tracked in real time, and the tremors have not stopped. The count has now passed 60 separate events. Most remain small, barely noticeable to anyone outside the instruments, but the pattern has grown more concentrated. Nearly every new tremor is appearing along the same geological fracture tracing the lake's western edge, the West Tahoe Fault. Scientists watch carefully as the intervals between tremors begin shortening. Instead of hours apart, some are now arriving only minutes apart. That change matters. Clusters like this sometimes happen when a fault is adjusting to new pressure conditions underground. Small movements relieve stress gradually, preventing larger ruptures, but not always. Sometimes these clusters mark the loading phase before a stronger release. Shortly after midnight, a new tremor registers. Magnitude 3.4. For the first time that day, people around the lake clearly feel it. Windows rattle in South Lake Tahoe. A few residents step outside their homes, scanning the dark horizon. Phones begin lighting up with social media posts asking the same question. Did anyone else just feel that? The shaking lasts only 2 seconds. Then silence returns. Inside the seismic center, analysts zoom in on the event's location. It sits directly along the West Tahoe Fault trace, almost exactly where the earlier microtremor cluster began forming hours earlier. More concerning is the depth, shallow, very shallow. That means the movement is happening closer to the surface fractures that define the Tahoe Basin. Hydrologists run updated models one more time. The lake level still reads 6,229 feet. Snowmelt continues pouring into the basin from surrounding mountains, and the enormous weight of water pressing down onto the lake bed has not yet stabilized. Scientists cannot say for certain what will happen next. Maybe the tremor cluster fades. Maybe the fault quietly releases the extra stress and dozens of small movements. Or maybe the pressure building beneath Lake Tahoe is still searching for a larger way to escape, because faults that have slept for thousands of years do not always wake gently. And tonight, beneath one of America's most beautiful lakes, the ground is still moving.